Hi ladies and gentlemen, so today we're taking a look at 3.2, which is multiplying polynomials and then utilizing Pascal's triangle when multiplying out binomials with really high exponents. So first up, let's start with the warm-up problem, getting a little bit of review with some addition and then some review with the multiplication that we've already been doing this year. Take a moment to pause the video, press play to see the answers. Alright, so with number 1, adding 4x squared plus 3x plus 3 and 2x cubed minus 6x plus 9. Combining our like terms, starting with our highest degree exponent because we want this written in standard form. We have 2x cubed, and there's nothing to be added with that. Then we have our x squared. So we have a 4x squared and nothing to be combined with that. After that, we have our x variables. I have a 3x and a minus 6x, which would give me minus 3x. And last are the constants. I have a plus 3 and a plus 9, which would give me plus 12. Taking a look at the multiplication. When multiplying, as we've done in the past, we need to work on distributing all the pieces from the first quantity into all the pieces from the second. So x times x is x squared. X times negative 10 is negative 10x. Multiplying the second number in, 3 times x is 3x. 3 times negative 10 is negative 30. After that, combining any like terms we have, that'll give us a final answer of x squared minus 7x minus 30. So the objectives for today are multiplying polynomials and then using binomial expansion, which is applying Pascal's triangle, to solve binomial expressions that are raised to really high exponents. So multiplying polynomials is just like we did in the warm-up, but on a little bit more of an extreme level. There's a couple of ways you can organize your work when multiplying polynomials, and that's going to be the thing that you want to become really comfortable with is whatever method you do use to organize your work because these problems can be really easy to get lost in the numbers and accidentally make a small mistake. So make sure you're staying organized. Example 1. So the first method I'm going to show you of how you could organize your work is using the distributive method. So I'm going to write that at the top. So I'm just going to show you what the distributive method or property would look like when multiplying polynomials. The first thing we're going to do is we're going to take this first term and multiply it into everything in the second quantity. So a times 2 is 2a. A times negative 5 is negative 5a squared because a times a is a squared. A times a squared is a cubed. Then I'm going to take this second number and I'm going to keep the sign that's in front of that number. So I know it technically says minus 3, but when I'm multiplying it in or distributing it in, I'm going to look at it as a negative 3. So negative 3 times 2 is negative 6. Negative 3 times negative 5a is a positive 15a. And negative 3 times a squared is negative 3a squared. So now that I've done the multiplication piece, now I need to combine my like terms and get this in standard form. So the first thing I'm going to do is look to see which terms have the highest degree. I have a positive a cubed and nothing else raised to the power of 3, so that's going to be my first term I write down. Then from there, I notice I have a negative 5a squared and a negative 3a squared. Combining those, that will give me negative 8a squared. Then I have a positive 2a and a positive 15a. Combining that is going to give me a positive 17a. And last, looking at my constant, I only have a negative 6. So on the very end, I'm going to say minus 6. All right, so this is looking at using the distributive property. And for some, you've been using this method for a while, and that's going to be your favorite. For others, you might like this next method better. So in example 2, I'm going to show you how to display your work or organize your work using what's called the box method. You might have used this method in the past and called it something different, but the process is still the same, and I just want to show you that this is another way to organize your work. So the way that this method can be applied is I'm going to create a box, and I'm going to have one box for every term in each quantity. So for example, my first equation is y squared minus 7y plus 5, so it has 3 terms. That means I'm going to create a box with 3 columns. Next, I'm going to create a box with the number of rows depending on how many terms my second equation has. So my second equation is y squared minus y minus 3. So I'm going to create 3 rows as well. And what I'm going to do is I'm just going to multiply all my terms by each of the numbers outside of my rows and columns. So starting off, I'm going to take y squared times y squared to get y to the 4th, y squared times negative y to get negative y cubed, y squared times negative 3 to give me negative 3y. So I'm taking that top number from the first column and multiplying it by each of the terms for each row. And I'm going to continue that process now with negative 7y. So negative 7y times y squared is negative 7y cubed. Negative 7y times negative y is a positive 7y. Notice that if it's positive or negative, especially with negative of course, but when it's positive, I tend to put a plus sign in front just to remind myself that that is a positive number. Negative 7y times negative 3 is a positive 21y. Oops, and that one above should have been y squared. Now moving on to the last column, 5 times y squared is a plus 5y squared. 5 times negative y is negative 5y. And 5 times negative 3 is negative 15. Using this method, when it's a perfect square, meaning this is like a 3 by 3 box, and your rows and columns are the same, and it's the same terms, a really neat thing happens. My like terms end up in these diagonals together. So that only happens when the two quantities are multiplying together are organized the same with the same degree terms. So it doesn't always end up like this, but in this specific problem, it creates this nice, neat diagonal set for us. So combining like terms, we end up with y to the 4th minus 8y cubed. And then we get plus 9y squared plus 16y, and then minus 15. So I ran out of a little bit of room here. I wrote a little too big. So let me write a little bit smaller here. There we go. So you could have multiplied this out using the distributive method or using this box method as well that I just showed you. Either method works for organizing your thoughts and your work on this, so whatever makes the most sense to you is going to be perfectly fine with us.